Okay, we're back, and we need to take a look at these example problems. You know me, like I said before, over and over, I'm the example king. All right, so let's take a look at A. It says, what nucleophile would you need to form the following compounds as a result of 1-iodobutane? All right, so 1, 2, and 3, and 4, and then off of that fourth one, I have an iodo group. All right, so I'm just going to make this very simple and easy and quick because I know that's how people like it. 1-iodobutane, we've got 4 carbons, right? All right, so 1, 2, 3, and 4. There's the 4 carbons. 1, 2, 3, and 4. There's the 4 carbons. Do you see what I'm doing here? 1, 2, 3, and 4. There's the few carbons. 1, 2, 3, 4. There's the 4 carbons. Guess what? 1, 2, 3, 4. There's the 4 carbons. And then 1, 2, 3, 4. There's the 4 carbons. So those 4 carbons are coming from the iodobutane piece that they wanted me to start with in the very beginning of the example problem. Now it says, what nucleophiles would you add on? It's what I didn't put in parentheses. Okay? That's all there is. So if I wanted to take this and I wanted to react it with OH minus, that will put that piece on instead of the iodo group that is on there right now. Here, I'll do the O, and then off of that is a CH3 group, a methoxide. Here, I've got a NH with a CH3 group. There, I have an SH group. Here, I have a S, CH2, CH3 group. And then there, I have an O with a carbon, double bond O, and a CH3 group. Folks, that's all there is to it. Those are the nucleophiles that I need to bring in to substitute for the iodo, which is a halogen in these reactions. This is what substitution is. I mean, that's really all that it really is. It's just the differences in the mechanisms and trying to pick out which one is going to be more preferred, SN2 or SN1. That's really all that this is about. All right, so let's take a look at another example. Here we see a question and it says, fill in the squares. Tell me what is needed in order for this to happen. Okay, so let's take a look at A. If I look at A, there's the alkyl halide. They want to know, what do I add with it in order to get this as a product? Okay, so 1, 2, 3, and 4 carbons. 1, 2, 3, 4 carbons. So it looks like they've taken the bromo off. They've replaced it. They've substituted it, and they've substituted it for something. What did they substitute it for? Well, it looks like I need an OCH3 group, doesn't it? Okay, so OCH3 is what needs to happen there. Now, I want you to think about this. This is a primary alkyl halide. Primary alkyl halides only undergo SN2, which means that carbon is only a cheater. I want you to start assigning that to each one of these questions as we go forward. All right? That's very important. We're going to start establishing those connections with these example problems, and that's how we're going to start doing them. So if this carbon is a cheater, then that's okay. The primary alkyl halides will allow that to happen. Not restrictive. That OCH3 is going to come in, it's going to cheat, and then that bromine is going to leave, and off it goes. Next is B. What do we add with OCH3 in order to get this type of molecule? And uh-oh, look at that. They're showing me some stereochemistry. I've got to be careful. Okay, so this is how we do it. 1, 2, 3, 4, and 5, right? Okay, so 1, 2, 3, 4, and 5. It looks like this is where the OCH3 is going to go. So that probably means that this is where bromine is going to go as well. Okay, so if that bromo is there, the bromo is going to leave. The OCH3 goes on in its spot. This is a secondary alkyl halide. Secondaries undergo SN2s and SN1s, right? We said it can do both, but we said we can sweet talk them. We can whisper things, pss, 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 right? Well, what do we whisper here? We whisper a very attractive friend. And we say, hey, I want to introduce you to somebody that I know. And then we go over and we introduce them, and then we hope that that carbon decides to pair up in that relationship as fast as he or she can. So by choosing a full-blown negative, we are helping ensure that a SN2 reaction happens. Why am I talking about that? Because this is a dashed bond. And if SN2 happens, that carbon's got to cheat. And if that carbon cheats, it can only cheat through the back door. So Walden inversion is going to be very important here. So that means that this bromine needs to be on a solid wedge. So when the carbon cheats and OCH3 comes on through the back door, it's going to flip that stereochemistry, and what was pointed toward me is now pointed away from me. So they showed me stereochemistry in this example, and that is why we have to show stereochemistry in our starting reagent. All right, now C. Let's take a look at it. See, they give me this compound. They give me a ring. They give me this product, making me think that this is difficult, but it's not. All right, so I get the ring structure. So all of this, pretty much the same. Look at that, right? So I've got this chloro group that's pretty ugly. And it's going to say, chloro, you got to go. I'm just tired of you looking at you every morning, waking up, and then turning over and seeing your awful face. I just can't deal with it anymore. So chlorine, you got to go. So what do we add to this that is maybe a little bit more attractive to take the spot of chlorine? Well, what did you put on chlorine's place? That's all that you got to do. So you've got this oxygen, and off of this oxygen, you've got this benzene ring with the delocalized system in the middle of it. So that's all that there is to predicting this substitution product, folks. That's it. Now let's look at D. If we look at D, we have this C triple bond N, and we get this product here. All right, so it looks to me like this is the spot that C triple bond N went on to, which means that that spot better have had a halogen on it. Well, we also get this CH3 group that's down here. That CH3 group did not really play a role in anything at all. It's going to stay the same. They give me stereochemistry on that, so I'm just going to keep it the same stereochemistry. That really has nothing to do with the reaction at all. What does have something to do with the reaction, though, is this bond, because that's probably where a halogen like chlorine was at some point in time. Or I could have put a bromine there. Same thing up here for part B. I wrote a bromine. I could have put a chlorine there. It doesn't matter. As long as it's a halogen and it can leave, that's all that matters. I could put an iodine on it if I wanted to. But here's the kicker. You know, this chlorine right now is on a secondary. That secondary position is either SN2 or SN1. I've got to be able to control which one goes forward, and it looks like I've picked this full-blown negative thing. So very attractive friend. I'm going to persuade it to cheat. All right, so that means SN2 is going to happen. Well, if this nitrile group, C triple bond N, is pointed toward me, what it needed to be beforehand is going to be a chlorine with a dashed wedge. And that is ensuring that Walden inversion will take place. It was pointed away from me in the beginning. Carbon's going to cheat. Nitrile will go in, switch places with the chlorine by sneaking through the back door, and it will flip the orientation from backward to forward. So that's the thing with SN2. Part C, we didn't do an SN1 or an SN2 here. I forgot to do that. So that halogen is attached to a carbon that's attached to two others. So this is secondary, which means SN2 or SN1 can happen. And I'm promoting SN2 to happen because I'm picking out a very good negative nucleophile in order to do it. All right. Here's another example. Which of the following is more reactive in an SN1? And for part A, they give me two choices. Which one is it going to be? All right, so let's think about this for a minute. Which of the following is more reactive in an SN1? So that means SN1s are not going to be cheaters. Okay, no cheat. We need to think about carbocation stability here. They need to be on their own. All right, so this bromo group, right now, if that goes away, a carbocation would form. This bromo group, right now, if that goes away, a carbocation would form. So what's the differences between these carbocations? That's what we're after. All right, so over here to the right, I get a carbon to the left and a carbon to the right. Okay, so that's secondary. And then here, I go up, I see a carbon to the left and a carbon to the right. So that's also secondary, right? Not quite. Let's take a look at the types of secondaries that they are. Look at this. Here's a carbon that has a double bond, pi set of electrons. And right next door is a carbon that will have a positive charge. That's called delocalization, folks. So this ring is delocalized. But if that carbocation stays at that carbon right there, the neighbor, then that delocalization can go into the chain and then come back around. That improves the stability. This is called the benzylic carbocation right there. This is just a normal run-of-the-mill secondary, which is perfectly okay. Perfectly okay. But benzylic is a little bit more stable than the secondary because of the delocalization. Because of that, that carbon is more prone to be on its own. Because of that, that carbon is more prone to be an SN1, a non-cheater carbon. That's what this is about. So for part A, it's going to be this one. Let's look at for part B. For part B, if we get rid of this bromo group, the carbocation is going to be there. If we get rid of this bromo group, the carbocation is going to be there. So the question is, which one would be more prone to kick that off first or the quickest? Because we're talking about SN1s. We're talking about carbons being on their own, forming carbocations before the nucleophile comes in. Well, let's compare the difference between the two. This carbon here, if you didn't know any better, you would go carbon to the left, carbon to the right, secondary, and then you would look at this one and say carbon to the left, carbon to the right, and you would say secondary here as well. And you would say, well, there's no difference. Well, yeah, there is. There is a difference. The reason that it's a difference is how on earth can this carbon hold really strong negatives with a positive? This is actually not a secondary per se. This is really a Benzylic. We've talked about the problems with Benzylic. We actually said that Benzylics couldn't even undergo SN1s or SN2s. This carbocation, the carbon, folks, it's messed up. It's messed up in the head. It's got a positive and some negatives. No. Nuh-uh. You don't want nothing to do with that carbon. You better go away and you better run. You better run as fast as you can and you never come back. Benzylics are bad. This one, though, that carbon beside of it is a carbon double bond. This is an allylic. Allylics are like benzylics. There's delocalization that can take place right in here. We can see a flip-flop of that double bond. We can see a movement of that carbocation when it forms. Pi's move to positive charges. That was what delocalization was all about. Because of that, it stabilizes the molecule and it allows that carbon to be more comfortable carrying a positive charge that we call a carbocation. So that is a secondary, but it's an allylic. So this one would undergo an SN1 reaction faster. Now let's take a look at question 2. Question 2 says, which of the following is more reactive in an SN2 reaction? All right, so SN2s cheat. That's what we got to keep in mind, right? So which one of these carbons would be more prone to cheating? Okay, so let's take a look at A. Here's my bromo group. This is the carbon that we got a big question mark behind. You want to date that carbon? If not, you better identify it the right way so you don't date it. So this carbon has an ethyl group and a methyl and a hydrogen. And this carbon has an ethyl and a hydrogen. This carbon got bigger houses around it, right? So if we had a nucleophile that came in to each one of these compounds, it's going to have an easier time going in and cheating with this particular carbon right there to the left. And the reason is because, yeah, they're neighbors, but this is a smaller house. And if it's a smaller house, you might have, a little bit more land to kind of sneak behind the bushes and the trees and stuff before you go through the back door. Versus this one, which is a much bigger house, and there's not that much wiggle room in there to hide and sneak and peep. Well, this one would react faster in an SN2 reaction. Keep in mind, this is secondary, but this one, folks, it's also a secondary. So no difference in the carbocations there. It's the neighbors that are around it that helped us make this decision. Next one, B down here at the bottom. We have this bromo group on this ring, and then we have bromo on a carbon on the ring. Okay, so which one of these could SN2 happen the fastest with? Okay, well, I'm going to kind of stop you right here because this bromo group is on a benzene ring directly, right? If we had a nucleophile that tried to come in to that carbon and cheat, that carbon is going to say, oh, because you're going to disturb a good thing that I've going on here. This is delocalization around the ring. This is actually the aryl carbocation that we talked about in the last video. When these halogens are directly attached to these resonance rings like this, folks, this negative source of electrons, these are the X's. Remember, that nucleophile is going to come in and go, whoa, no, and then turn around and go back the other way. So this one is going to happen much faster, and that's because the negative area of the ring pushes it away in the first molecule. In the second molecule, that carbon's a little bit further from that ring, and it can go in and cheat with that carbon a little bit better. It has a better opportunity of doing it. All right, so there's 1 and there's 2. One focused on SN1, one focused on predicting stability of SN2s. Hopefully you were okay with that. If so, then, I'm slowly chipping away at the substitution wall that a lot of people put up and a lot of people cannot ever get over. Let's take a look at problem 3. This one says, draw the products of the following reactions showing the stereoisomers that are formed. Okay, so let's see how we solve this type of problem. Here I've got a molecule. This molecule has a halogen. Right there it is. Ta-da! Bromine. And it looks like I've introduced a very pretty friend. And this very pretty friend is an OCH3 group. So what do you think is going to happen? Well, what we hope happens is that bromo will leave. Poop, off you go, ugly thing. And then OCH3 will come in to play. That methyl group does not get changed. All right, well, that methyl group never got touched, so that's still a positive wedge, or a solid wedge. But I've got to keep in mind here, okay, this bromo group is secondary. That's secondary paired, and that means SN2 or SN1. Well, what we've done is we've preferred SN2 to go forward because we've picked a very strong, pretty nucleophile to come in. So that means Walden inversion will happen. So if this bromo in the beginning was pointed toward me, then that means that this incoming group now has to be pointed away from me because it snuck through the back door and it flipped the stereochemistry at that spot. Again, methyl, nothing happens to the methyl group. Nothing happens to the methyl group. It doesn't get affected. It doesn't take part in the reaction. What was there before is what's there after. It's only the bromo group that's getting switched. Now let's look at part B. All right, so for part B, it looks like this bromo group right there is on a carbon. This carbon is really a benzylic carbon, right? So a benzylic carbon, and that benzylic carbocation can undergo SN2 and it can undergo SN1. Now, we can persuade it to go one route or the other, and one of the ways that we do that is introducing a nucleophile. What kind of nucleophile did we introduce? Is it a very pretty one? And the answer is no. I don't see a full-blown negative on it. So this is a very weak nucleophile, which means I am trying to persuade carbon to go forward and be single for a little bit before it gets back into its relationship. So let's just keep that in mind when we begin to draw this product. So I'm going to redraw the reagent first. Again, it's something that I always do. I think it helps me, and I hope it helps you too. So that's why I do it. So here's what we started with. That bromo group is going to leave. Carbon's going to say, I had it. You got to go. And that forms a full-blown carbocation at this point. That full-blown carbocation now has some time to rearrange. The question is, does it? And the reason is a SN1 has been preferred here because of what we picked. So carbon's going to be single. Carbon's going to look to the left. It's going to look to the right and say, you know what? There's nowhere else I'd rather be. This is a benzylic carbocation. If I go right-handed, that's a secondary. I'm a little worse off. If I go left-handed, yeah, that's a tertiary spot, but I interrupt the delocalization there. And that's not really a tertiary spot. It doesn't want me to do that. If so, the whole ring gets destroyed. So I can't really move left-handed. So that's where it's going to end up. All right, well, if that's the case, then that carbocation's not going to move, and that means the incoming group is going to go on into that spot. And like I said before, think about alkene reactions. Just erase the hydrogen. Your negative piece would have been the O and the CH3 group. You added H on first. That was the positive. H plays with other H's. And then you added on the negative piece, which was the OCH3. That's what we do here. As far as stereochemistry goes, it didn't really give me insight into stereochemistry right there. So I'm probably not going to worry about that in the product side of the house either. If I do want to worry about it on the product side of the house, I'm going to say that it is a mix of R and S. Okay? And I'm going to say it's a mix because, folks, I have no control of it. SN1 is not going to go through the back door every single time. Sometimes it does, but sometimes it goes through the front door. This carbon's not a cheater. There's no sense in it sneaking around. It doesn't have to. Sometimes it feels like it, though. You know, maybe it just drove up behind the house and parked in the parking slab, and maybe the back door is the quickest way to get into the house to get its thing going on. Who knows? That's just how molecules are. Who would have ever thought? Who would have ever thought I'd be talking to you this way in organic chemistry, right? Of all things. Now let's take a look at C. Oh. Do you remember what C was? C is a Fischer projection. I thought we were over this. No, we're not over it. They're showing me stereochemistry here. Okay, so they're showing me stereochemistry with part C. That is a Fischer projection. I'm going to have to go back and I'm going to have to remember what Fischer projections were. Okay, so let's do a quick review of a Fischer projection. So here were the rules of a Fischer projection when we talked about them back in the day. I mean, it seems like back in the day, but it was probably very recent. Who knows? But it says if the lowest priority is on a vertical bond. So a vertical bond, of course, goes straight up and straight down. And the lowest priority typically is hydrogen, but it doesn't have to be, just whichever one has the lowest atomic number. If it goes clockwise, it's R. And that's kind of what we would expect. And if it goes counterclockwise, it is S. And again, that's kind of what we expect. Well, if we go back and take a look at this problem, here we go. Hydrogen, which is the lowest priority out of the four. Folks, that's not on a vertical bond. That's on a horizontal bond. That goes left and right. So what does that mean? Well, if the lowest priority is on a horizontal bond, it means you assign the direction R or S as you see fit, as you did before, but we always have to pick the other answer because it's going backward. That's what I have to remember. It's going backward. All right, so left and right like this. Okay, so this is how we do it. Out of the three groups that are here, which one comes first? And you're going to tell me bromine. I know you're going to tell me bromine. I know it is. And you're going to tell me why? You're going to say, because it has the higher atomic number. Okay, so there's bromine, group number 1. All right, then we go a carbon and a carbon. That's a tie. And then we move on to the next, and that's another carbon, and then that's a carbon, or nothing, that runs out. So this is group number 2, and this is group number 3. So group number 1, group number 2, group number 3. Look at that. That is clockwise, isn't it? So traditionally, this would be R, but because hydrogen is on a horizontal bond, we flip it, and we need S. That is the S position right there. Why am I doing this? Because we have introduced a very good nucleophile. This bromine is going to be tertiary, and this could be playing a factor in our product formation. Now, let's take that information and let's kind of go with it. Okay. Bromine, sorry, I said a tertiary position a while ago. It's not. This is secondary, right? There's a carbon to the left or up above, and there's a carbon down below. So that is a secondary, which means SN2 or SN1 can happen. Which one's going to actually happen, though? Well, we're whispering sweet nothings. And we've brought in a very attractive friend. And we hope that our friend is going to cheat. I mean, that's what this is about. So that OH group is going to persuade an SN2 to go forward. That carbon is going to cheat. So I'm going to draw my reagent just like it was drawn in the beginning. CH3, CH2, CH3, hydrogen, and bromine. I want this carbon to cheat, so that bromine is going to leave, and it's going to get replaced by the OH group. That was my nucleophile. Now, SN2 happened, Walden inversion happened, which means stereochemistry flipped here. So let's take a look at the stereochemistry. This is a S form right now. So that means I need to make sure that I get a R form. That's SN2. Well, right now, OH is 1, ethyl is 2, methyl is 3. Here we go around the rosy. That is a clockwise rotation that normally would be R, but because hydrogen is in the horizontal fashion, I need to pick S. It's still S. This is still an S form. Well, I need to go through and I need to make sure that I represent the other. I need to represent R because Walden inversion. The only way that I can do that is if I pick 2 of these groups and just flip them. That's all I need to do. All right. So I don't want to tackle that H group. That's kind of making my decision, right? So I'll pick 2 other groups, and I'll put the OH here, and I'll put the CH there. So now what we have is OH, ethyl, methyl. So now we get this rotation. This would be normally S, but hydrogen is in a horizontal bond, so I pick the opposite of, and this is a R group at this moment. So folks, there's the structure of this one. It's a Fischer projection. We don't do a lot of examples of those. It was a kind of a good review maybe. But again, Walden inversion, SN2, stereochemistry, all wrapped up into one. If we look at D, here's the halogen group, right? That halogen's on a carbon on 2 others. So this is secondary. So SN2 can happen, SN1 can happen. All right, so which one's going to be preferred? What have I decided to whisper to it? Well, I see this group. Do you see a negative on it? I don't. That means it's kind of ugly. Not the ugliest, but I'm not bringing the most attractive friend over. So that carbon doesn't feel the need to cheat. So this NH2CH3 is a poor nucleophile. Still going to replace chlorine. But it's a poorer nucleophile than what I could have picked. And because of that, I am promoting an SN1 here. Which means CH3, CH2, carbon, CH3, and then I get this solid bond with chlorine, and then I get this dashed bond with hydrogen. Well, there's my starting reagent. What goes on? Well, my chlorine's going to go away. a carbocation is going to form. Does the carbocation shift? If it goes left, it's secondary, that's silly. If it goes up, that's primary, that's even sillier. So it's going to stay right there. So just in case it needed to, it could. Right there was the option. And now that chlorine's gone, that will make room for this group. But keep in mind, one of these hydrogens has to go away. I need a nucleophile here. So just like before, H goes on first, if you want to think of it that way. And then that leaves a NH CH3. Now, this promotes an SN1. So, SN1 has that stereochemistry, but it could also go through the back door if it wanted. I mean, that's no big deal. It could do that. So, here's CH3, CH2, and then here's CH3. There's NHCH3, and there's hydrogen. Well, what I could do here to make sure that, because the directions tell me, show stereoisomers that are formed. Well, I need both. SM1 can give me the same stereochemistry, or it can give me the opposite stereochemistry. There's no rhyme or reason. So it tells me I'm going to have to show all the forms. So I'll just pick two groups, and I'll just switch them. So this will ensure that I give you the R, and it helps ensure that I give you the S. Now, let's look at part E. As far as part E goes, we get this double bond and a bromine on it with the OH group. This is one of those problems that I told you that you would probably never see on a test. I wanted you to see one of them in actually person, though. A lot of people would look at this and say, all right, so bromine's going to go away. This is an allylic carbocation, so SN2 and SN1 will both happen. We're picking a poor nucleophile, so SN1 is going to be driven forward. And this bromo is going to be replaced by an OCH3. Yeah, that's great. So there is one choice. But, folks, you also have this double bond that's in here as well. And this double bond is going to create a negative area. And this negative area is kind of right beside of a carbon as well. And there's other products that could happen here. So you just got to be careful with these. And that's really where I'm going to stop this example. I'm not going to go any further because I wouldn't expect you to go anywhere any further either. So in the next video, I'm going to continue on with these example problems. And this will be the last one. And I just want you to kind of scribble these down. Again, take a stab at them. See if you can kind of pick out what the correct answer is. And then we'll sum up this example problem and sum up the substitution lecture in the next video. So question number 6, for each of the following pairs of SN2s, indicate the one that occurs with the greater rate constant. That means the fastest. All right, so I'll leave you with that example. See if you can answer them. Push play on the next video, and we'll finish up the substitution lectures. Can you believe it? Not as many videos as you were expecting, was it? At least I hope not.